And today we're going to start a new chapter, chapter 6. Oops. And it's we will get into actually the nuts and bolts of the class, in a sense, because we are talking about transistors today. So we'll learn about the basic kind of the transistor, which of course is the unit of any integrated circuit or electronic. Oh, also I posted all the notes last night, so you should have it for the whole week, most likely. Okay, so you can print it out, bring it, as someone suggested. Okay, so we'll talk about transistors today. In particular, we'll talk about what are called field effect transistors. Now, field effect, oh, sorry. It's turned on. Okay. Historically, field effect transistors were not the first ones that were invented, but they are the easiest to understand. So we'll start there. And then we'll talk about other kinds of transistors. And they're very important today, as essentially shown by this news article, which I mentioned last class, from the New York Times from last year, about a year ago. Okay? This essentially is an article about Intel in Portland working on their next generation devices. So typically the devices go from research to production in about 18 months or so, year and a half. So this will be coming up to production if everything is on schedule. And I don't exactly know if it is, but assuming it is. Okay, here they are trying to essentially increase the density of the circuits. So in your same area of the chip, they're trying to pack more transistors in. And the goal there, of course, is to have more computational power. So you can have faster processing. If you want to do online gaming or whatever, right? Online streaming of video, you need to process lots of data really, really fast. And one way to do it is to, of course, make the transistors themselves faster. Another way to do it, of course, is parallelize the operations and use more transistors. Okay? And they're doing both. This is the second part, where you're putting more transistors into the same area. Okay, in this particular case, and we probably won't talk about it in the class in much more detail, they're trying to make three-dimensional transistors. Typically, transistors are two-dimensional. They're on a surface. In this particular news article, if you actually read it, they're talking about making it in the bulk of the material, so in 3 dimensions. So obviously, that helps you to put more transistors in the same area or volume in that case. Okay? And I would recommend you to read it, because it's an interesting read. It tells you an idea of where the industry is, about 12 months ago or so. Okay? And they're talking about field effect transistors, which is what we're going to study today. So this is the device which you'll learn today, which will come out in your laptops, phones, whatever, probably next year or a year from now. So it's very important to understand the physics of what's going on so you can understand what's coming out and hopefully make a contribution to the field. Okay, so what is the transistor? So let's abstract this a little bit, because all of us talk about transistor, but what does it really mean? A transistor in general, and there are lots of different versions of this, but from a very abstract point of view, the transistor is a 3-terminal device. Okay, so I basically drew a box. You have an input and you have an output. Okay, so far so good. It's pretty straightforward. And you have a control terminal. So you have 1, 2, 3. Okay, and we'll see what those mean. That's the, I would say, very basic definition. Okay, so you should at least know that. 3 terminals. Now, what does it do? Okay, it does 2 functions in particular. It acts as a switch. And this is something I'm sure you've heard before. A transistor is a switch. Why? Because in all computers and phones and so on, we do digital logic. We do digital processing, right? You have ones and zeros. And how do you create ones and zeros? You have a switch. 1 is on, 0 is an off, and so on, right? So it's kind of a logical way to think about what a transistor is. It's a switch. Okay? For a switch, a simple way to understand it, and this is not necessarily how it will be, but a very simple, I'm abstracting this in a very qualitative manner, is if you have a 1 coming in, you can think of the switch as on, a current flow, so input, output, you have 1 bit, let's say. Okay? So it's also a memory, right? You can think about this also as like a memory as well. Memory devices we'll talk about towards the end of the class. And if you have a 0, it's an off. No current flows, so there's nothing out here, so that's a 0. So you can kind of think about it as well. So that's a switch, just like you turn the light on and off. Okay, but these things can be switched, of course, billions of times a second, and they're very small and so on, right? So, and you can use a large number of these to create logic circuits, AND gates, NAND gates. I assume you've learned some of this in your digital design classes before. Okay. Of course, there's another application which is more important for analog processing, which is amplification. Again, I highly abstracted this. We'll talk about the actual amplifiers later on. And this is an op-amp, right, to some extent. You have a signal coming in. It gets amplified as it gets up. And there are many reasons to do this. Of course, for signal processing, it's pretty obvious. You want high signal-to-noise ratio. You need image processing, things like that. So any kind of analog processing requires this function. And again, like I said, I highly abstracted this out. So don't take this literally, but you can imagine something like this, a black box, some signal coming in. You apply some sort of gain. So that's your analog control. Okay? And you get out some sort of amplified signal out. Okay? Just like, you can think about it almost like an amplifier from your op-amp. I mean, from your previous classes. Okay? In reality, it's a little bit different than this, but keep that picture in mind. So a transistor does switching and amplification. 3-terminal device, switching, amplification. So this is basically it. Okay? Now we'll show that from what we have learned so far, which is basically the PN junctions and the metal semiconductor junctions, we can build devices which are able to do this. They're very simple, actually, very straightforward, as long as you understand the PN junctions and the metal Schottky junctions before. So keep that picture in mind, and then we'll look at how this is done. Okay? Once you understand that, then everything else becomes very straightforward, in a sense. Okay? Okay. So, okay. Before we go on, let's understand how this amplification and switching can work again in a bit more an abstract sense, which is actually nicely explained in the text. So I recommend you to actually read through it fairly carefully. So let's imagine look on the left-hand side first. So let's imagine a circuit. Okay, very simple circuit. There's a battery. There's a resistor. There's some sort of device. This is our transistor device, as you will see in a minute. But it's only 2 terminal for the time being. Okay, 1 terminal is not connected to anything. And then you have a current flowing through. Okay, so you can apply Kirchhoff's law and write that equation. The total voltage is the voltage from the battery is dropped across the resistor and across the device. Okay, so it's pretty simple. Current times resistor plus VD. Okay, everybody is comfortable with that. Now, what's different here is that we will say that this voltage that's dropped across this device, which is a transistor, is nonlinearly dependent upon the current, which should not be too surprising to us, because in a diode it's a nonlinear relationship, right? So but keep that in mind. Okay, now this equation, if you draw on the current voltage curve, is essentially a straight line which looks like that. Okay, that's so-called load line. Okay, the slope of the line is a resistor, that external resistor that you applied. Okay, now the voltage-current relationship of this device, we postulate, it looks something like that. Okay, we will relate that to the PN junction in a second, but just assume that it looks like that. It's a nonlinear relationship. Okay, again, it's not so surprising, because we know from a diode that the current voltage relationship can be nonlinear, right? It's exponentially increasing the other direction, not this way, but the other direction. Okay, so it's nothing too surprising here. Now, to actually solve this equation, so if I actually write this equation out as a circuit, I have that, right? Now I told you that VD is some sort of ID is some nonlinear function of VD, right? And you can plug that in here, and then you get an equation that you have to solve. Of course, a nonlinear equation, so it's hard to solve, so you can graphically solve. That's what's shown here. So you plot that curve, which is the nonlinear function f. That's a straight line, and where they intersect gives you our operating conditions, the current and voltage across the transistor. Okay? So that's how you solve for a nonlinear element within a simple circuit. Okay, mathematically it's basically that. You plug it in, you put it in MATLAB or something, solve it. It's not that hard. Okay? So that's the steady state operating conditions. Okay? We only have two terminals. Now we'll introduce the third terminal. See what happens. Okay? So in this particular case, nothing happens, right? If you change the voltage, if you change this, this E, you move up and down on this curve, basically. Right? But this nonlinear curve really doesn't change. Sorry, if you change E, this line moves back and forth, right? So if I may draw this, so keep this in mind because it's become important in a second. Okay, that's F. Okay, and this is, let's say, some E1. If I change my E, this line becomes E2, right? Let's say I reduce the E. Okay? So now, so the operating condition now changes. It follows this curve, essentially. Okay, so first, okay, this is a steady state, right? If you change the curve, if you change the applied battery voltage, this curve just shifts up and down. Okay? You get the steady state conditions. Now, we are talking about a slightly different thing. We are going to introduce a third terminal where we apply a voltage to control this function here. Okay? And that is the basis of the transistor operation. Okay, so let's see how that works. So again, this now becomes a three-terminal device. You have one terminal there, and one there. So three. Okay. And there's a notation we'll come to in a second. This voltage across these two terminals is VD, capital D. Voltage across this terminal and this terminal is VG. So these two voltages determine all the inputs, voltage inputs to this three-terminal device. Okay. Okay. So, and we have the same situation as before. You have a resistor, your battery, and all this stuff. Okay. So now, if you look at the current voltage curves, you still have the load line, which is fixed now because it's a fixed resistor, fixed battery, so it's a fixed line. But now you have a family of nonlinear curves here, which are controlled by a control voltage, which is VG, okay, which is that third terminal. Remember, in my schematic, I had three terminals, one on the top, one on the bottom, one on the left. It's the left terminal that's controlling that curve. Okay. So in this case, VG is 0. The curve looks like that. VG is, let's say, 0.25, looks like that. 0.5 looks like that. 1.75 looks 0.75 looks like that. 1 looks like that. Okay. So it's just changing, and we'll see how that happens in a second. Okay. Now let's imagine what happens as to the current, the steady state operating current, as you change the gate voltage. You're not changing the battery, you're just changing the gate voltage. Okay, of course you can simply look at the intersection points, right? So when the gate voltage is 0, that's your current voltage operating condition. As the gate voltage is increased, it goes up. Gate voltage increased, goes up, goes up, goes up. Now notice, look at the numbers for a second. I went from 0 volts on the gate voltage to 1 volt on the gate voltage. Now if I look at the operating voltage across the transistor, which is this voltage, the drop across the transistor, has gone from about 10 volts to almost, let's say, 1 volt. Okay, that's a 10 to 1 reduction by just applying 1 volt change in gate voltage. Okay, that's amplification. I've applied a small voltage difference to the gate, and I've achieved a huge 10 times larger voltage difference across the transistor, across the VD. Okay? That's amplification. So it's different amplification than what I showed you in my schematic. In this case, if I go back and redraw my schematic, it would sort of, let me try it, would sort of look like this. Okay? Our output is essentially is that. And our input essentially is that. That's the Okay? What I would do here is I would put a small signal voltage on VG, which will swing these curves up and down, right? And I would expect to get a big signal swing in VD. That's the amplification. Okay? And it's different than what I showed you before because there are different ways to do this. This is voltage amplification. Okay? When we talk about bipolar junction transistor, there will be current amplification. So okay, keep that in mind. Okay? So that's the picture of amplifier. Okay? That's small changes in VG become large changes in VD, is amplification. But we can also think about the concept of the switch here as well. It's very straightforward. If the VG, by changing the VG, so if you can bring the curve, so this we stopped here, but if you make it more negative, you can assume that the VG can be brought, this curve can be brought really small, such that the current goes to 0, essentially. Okay, which we'll talk about in a few minutes. And it can be switched all the way up here by making the VG very large, positive number. Okay, so I can switch my current from 0, which is down here, to some large value. So it's a switch also. In this case, it's a current switch and a voltage amplifier. Okay? Of course, these things become important when we put this into circuits. Right now, we're just talking about the physics, so it really doesn't matter. So you have to think about where it will get applied. Okay? All right. So that's the basic, very abstract picture of what an amplifier is. What a transistor is, amplification and switching. Now we'll see what an actual device looks like and how these things come about. Okay, we'll start with the junction field effect transistor because that's the simplest device to study. Okay, it's pretty simple actually, as long as you know the PN junctions. The device has 3 terminals, as we saw before. Okay, and they have specific names. So you have what's called a drain terminal, D. There's a source terminal, S, and there's a gate terminal, G. In this particular device, there are 2 gate terminals, as you see, on the top and the bottom, and typically they're connected together. So it really is just like one. Okay? So you can think about that as one for the time being. Now, the structure of the device is fairly simple. It's essentially 2 PN junctions. Okay? So let's start from the bottom. So you have a P plus region right here. And then you have an N region. So here you have a P plus N junction. Okay? And then you have a P plus region up on the top. So you have an N P plus junction again. So it's basically 2 PN junctions sitting opposing each other. 2 diodes sitting opposing each other. Okay? But the key part is that the current flow actually happens between the source and the drain. The gate is the control voltage. So the current flow is actually like that, as shown by this yellow arrow. Okay? From the drain, current comes in, goes out through the source. The electrons flow the opposite way. Okay? The gate has no current. Okay? No current flows, only voltage. Okay, so first thing to remember is that this is a P plus N junction, either of them. Okay, so most of the depletion, remember we have a contact potential, we have a depletion region. Most of the depletion region, of course, is in the N-type region. Okay, we know that by now. And under normal operation, these devices operate under reverse bias, which means that you apply negative voltage to the P plus region, a positive voltage to the N region. So this junction is reverse biased. This junction is reverse biased. Okay, which means that you end up having a depletion region. Okay? Now you can see if I increase that reverse bias, the depletion region grows. We know that, right? Because carrier extraction happens. And if the depletion region grows, now what is the depletion region, first of all? Remember, the depletion region means that there are no carriers, right? It is not a conductor. It cannot conduct electricity, ideally. Which means that if this region is a reasonable conductor, okay, because there are electrons, N-type, This region is essentially an insulator because it's a depletion region. If this grows into this, you can see it will start to restrict the current. So the reverse bias voltage can be used to control the current that flows between the drain and the source. That's the physics. We know everything. We know everything to really understand this now. Okay? I'll reiterate that in a second, but let's go through it first. So the current flows from the drain to the source. The gate voltage is applied between the P plus and the N. It reverse biases it. Increasing the gate, increasing that reverse bias voltage will increase the depletion region, and it will constrict that channel through which the current flows, and it will reduce the current. That's essentially the operation of this device. Okay? Now, there are a few things to keep in mind. First is that the source is typically grounded, as shown here. So it's a very typical configuration. And the voltages are always with respect to the ground. So when we say gate voltage, it's the gate source voltage. When we say drain voltage, it's the drain source voltage. Okay, keep those things in mind. They will become important when we connect them together. Okay. Yes, so the depletion region growing here will, of course, change the resistance of the N channel and hence change the current. This region is called an N channel. It's a channel for the electrons to flow, essentially. Okay. And there's a nice animation here, which I posted online, which shows the principle. Okay, so essentially this is, okay, there's a drain voltage is applied. I mean, drain source voltage, there's drains on the top, source is on the bottom, gates on the left. Okay, that's the drain current flowing. VGG is the gate source voltage. As you can see, when that's applied, the depletion region came in here and constricted the current. It will reduce the current. Okay. Oops. So you can see that's the drain, that's the source, that's the gate. Applying that gate voltage, push the depletion region on two. They're connected together on two sides. A symmetric device pushes the channel shut, essentially. Okay, and you can actually turn off the current, as we will see next. So going back to my previous analogy, applying. So what's showing here is that everything is connected to the source. The source is grounded, so all the voltages are with respect to the source. So there's a gate voltage with respect to the source, drain voltage with respect to the source. If you apply a small signal on the gate, here, that will get amplified across the drain source, as we will see. And by applying sufficiently high reverse bias voltage, I can actually switch this current off. And you can access the switch. Okay? And switching the current off essentially means that the two depletion regions on the two sides meet. And then no channel exists. It's essentially like a switch. Turns it on and off. Okay? So that's the principle. So let's see how we can analyze it. If you look closely at the channel, which is magnified image is shown here. So you have the source, you have the drain, and the gate shown here. The N-type material is typically lightly doped, which means it is a reasonable conductor, but it's not a great conductor. So it's sort of like a distributed resistor. Okay, it's a resistor essentially. So you have current flowing through a resistor. And think about it that way. Okay. So if you look at the local potential in this channel and plot that as a function of the distance across the channel, the voltage here with respect to the source, of course, is 0 because that's the source. Okay? As you go across towards the drain, the voltage increases until you reach the drain voltage. Okay? So that's why it behaves like a distributed resistor. A constant current is flowing through here, and because the resistance is a constant, you expect there to be a constant slope in your voltage drop. There's a constant voltage drop, which is basically what that is. Okay? So on the drain side, you have a high reverse bias. On the source side, you have a low reverse bias. Okay? That becomes very important. So does everybody see that picture? When you apply a gate voltage, now we're just talking about the drain. Okay? The drain drain to source voltage here is high because that's whatever is applied from here. As you go across the channel, there is a current flowing, so there's a potential drop until you get to the source, where the source to source voltage is essentially zero, right? It's with respect to itself. Okay, so due to the current flow, there's a voltage drop from the drain to the source, and that's what, and you can approximate the voltage drop basically as a linear drop. Okay, and linear, the assumption, of course, is that you have a uniform current flow in a homogeneous material, which is a reasonable assumption. Okay. Now let's think about how this operates in a bit more qualitative manner. Okay, before we actually do the calculations. So let's look at the top left first. Okay. Okay. In this situation, you have a low drain to drain to source voltage, very low voltage applied, low current is flowing. Okay, and the gate voltage is essentially not important and zero. You can imagine it's zero for now. Okay, so you have a small depletion region, of course, because that's a contact potential, right? Yeah, it's PN junction under no bias. You have some depletion region. And it's constant across pretty much because the current is very small, so that voltage drop is pretty much negligible. Okay, so basically a constant depletion region here, current flow, electron flow going from the source to the drain, current flow going from the drain to the source. And if I plot the current voltage curve, it's essentially a straight line. Small current. Okay, it acts basically like a resistor. There's no gate voltage applied. Okay. At low current, the voltage drop from drain to source is small. Depletion region is the same across the channel. Now, when we connect the gate to the source, okay, we apply a 0 volt in this case. So this was basically the gate is not important because the voltages are really low. Okay? It doesn't matter what the voltage is. Now, we are connecting the gate terminal to the source such that the gate to source voltage, which we call VG, is 0. Okay, that's shorted. Okay. Now remember, this is P plus, that's N. When the gate to source voltage is 0, if this has a positive voltage on this end, which is the drain, remember the drain has a positive voltage, this end is now reverse biased, right? Okay, so let's think about this again. Let's look at this side of the junction for a second. This is the P plus, that's N. This is the drain voltage, which is some positive number, connected to the N type. The P plus region is grounded, 0 volts. So it's reverse bias, right? The P plus is 0, N is positive. So it's reverse bias. Because it's reverse bias, the depletion region grows. But of course, as you go across the channel, the voltage on the drain drops, as we just saw, because the resistor current flows, voltage drops. So it becomes less and less positive here, less and less reverse biased. So the depletion region decreases, the width decreases, as you expect. So you get this characteristic shape, which looks like a funnel. Okay? And of course, as the depletion region grows here, the current starts to saturate, because now you're eating, this is of course an insulator, so you're basically shrinking the area of this conducting channel. Of course, when you reduce the area, the resistance goes up, current goes down. Or the current increase goes down. The slope of the current voltage curve goes down. So this starts to saturate a little bit. This curve bends. Okay? So as current increases, the gate channel junction is more reverse biased near the drain than the source. This starts to limit the current flow. Now, of course, eventually, the logical step is that they meet. If you apply enough of a negative gate voltage. If you apply a negative gate voltage here, you're making it more reverse biased everywhere. Of course, near the drain, the two depletion regions at some point will meet, which means that the current cannot flow. There's no extra current that can flow, right? Because you've gotten rid of all the carriers there. All the current can still flow because the current comes here, and then there's a field here that sweeps it across. But no extra current can happen. So the increase in current with increase in voltage, the drain voltage, is essentially 0. In other words, you increase the drain voltage, nothing happens to the current. In other words, it saturates. Okay. So further increase in current pinches off the channel as the two depletion regions meet. Current doesn't really increase much further as voltages increase, so you have a saturation region. Okay. And that's called pinch off, because the channel is essentially pinched off. Two depletion regions meet, you get rid of the N-type region there. So you can clearly see the switching behavior here qualitatively, right? That's on, no problem. That's basically sort of like an off. We'll look at this more carefully with the curves in the next few slides. Okay. The amplification of it is not so obvious yet. Okay. But this is the basic principle I need you to remember. Just to summarize, you have a drain to source voltage. Okay, that's our input voltage. Okay. You have a drain to source current, which is our output current. Okay. And then you have a control voltage, which is gate to source voltage. In this case, that's 0. In all these cases. This case, it doesn't matter. These two cases, it's 0. Okay, so 3 terminals, 3 things that are important. Drain to source voltage, drain to source current, gate to source voltage. Okay? And here, we haven't applied the control at all. The control is 0. All we have looked at is what happens as you increase the drain to source voltage to the current. So we are looking at a specific nonlinear curve in that diagram that we saw before. So we had a family of curves. Okay? Now, next, we will start messing with the control voltage. And that, of course, will change this curve. And that's where the amplification really comes into play. Okay. So gate control. So previously, the gate voltage was 0. What happens when we apply reverse bias gate voltage? Of course, when you reverse bias the PN junction, it's pretty simple. The depletion region gets bigger, which means that one would expect a pinch off to happen at a lower drain to source voltage. Okay, you get a different curve. Okay, so as you apply, so the situation is as follows. The P plus regions are connected together. So this is connected to source. This is connected to source with the same voltage. So imagine these two terminals are essentially shorted together. So this is the gate voltage, VG. Okay, the source is grounded. The drain voltage is essentially drain to source, also with respect to ground. Okay. Again, we have 3 things we have to worry about: VG, the control voltage; VD, the input voltage; and ID, the output current. 3 things to keep in mind. So if you plot the ID, which is the output current, as a function of the input voltage, VD, for different control voltages, you get a family of curves. Okay? This is as you increase the negative voltage on the gate, you make this more negative, of course, the depletion region pushes more in, which means that the pinch off will happen at a lower drain voltage. Right? Remember, if I make drain voltage more positive, this is getting more reverse biased, right? This is going to pinch off. But the point where the pinch off happens, so let's say at VG equals 0, this is what we saw. The pinch off happened at this drain voltage. Okay, but if I apply a negative voltage on the gate, you start off with some reverse bias, then the pinch off happens at a smaller drain voltage. Okay, and you increase the gate again, happens at an even smaller drain voltage, and so on and so forth. Okay, now of course you can compare this to the previous family of curves that we saw and see how amplification happens. Okay, it's exactly the same way. For a small change in the gate voltage, I'm going from just 0 volts to 3 volts, I get a huge change in the drain voltage. Okay, I don't have the load line here, but you can imagine. Under saturation, drain current. Sorry, no mistake. So the output, of course, is the drain current, not the drain voltage, right? So let me reiterate. Sorry, I made a mistake there. So when you apply, when you change the gate voltage, say from 0 volts to minus 3 volts, the output, which is this saturated current, goes from a very large value to a very small value. And that's amplification. And of course, if you extend it even further, that becomes switching, right? You can essentially go from very large current to basically zero current. So you can see how that happens. Okay. So beyond pinch-off, the gate voltage controls the drain current, not the drain voltage. So that's also important. In other words, if you look at the curve here, it's basically flat. Okay, so this input voltage doesn't do anything. It just holds the voltage. The current is essentially switched by the control voltage, VG. Okay. So just to reiterate this, by going making the gate voltage more negative, you are reverse biasing the junction more. You allow the pinch-off to happen sooner than it otherwise would, and that allows you to constrict the current and essentially reduce the current. And that's where the amplification happens. You go from very large current to very, very small current, switching and amplification. Okay? The amplification, of course, is the picture is that if you apply a small signal AC voltage to the gate, so the gate is essentially switching between these curves, which is what I showed here. Okay? So instead of being a voltage now, I will be looking at current. My current is the output. So here is IP. It's my output signal. My input signal is still VG, small signal, and amplified output in the current. Okay? What I drew before is still correct. It depends on the device. This particular device, this is the situation. You have to be careful when you analyze it. For JFET, this is the case. Okay? Now, of course, the next question is how do we quantify this? So we draw these curves, but what we really want is we want some equation that predicts, okay, if my gate voltage is this, if my drain voltage is this, what is my current? Okay, then I can calculate the amplification factor, how do I control amplification, how do I switch, how fast do I switch, things like that. This is what's important when you make a transistor. So let's quantify this. And it's very easy because we've done all the math already. So this is nothing, should be nothing new to you because it's a depletion region. Okay? So let's look at the geometry first. It's not too complicated. It's same thing. Here, this coordinate is x. Start at 0 at the source, go to a channel length L, okay, at the drain. And this is, of course, a cross section. So you have a total channel width of A, as shown here, which goes from the center of the channel to the transition region to the P+. Okay. W is the width of the depletion region, which locally changes across X. H is the remaining width in the channel, which also changes locally across X. Okay, so pretty simple. And the voltage we saw before changes from VD to 0. And it's non-linear, it's not a linear curve, but we'll come to that. Okay, the first equation is something we know. It's basically what is the depletion region at the drain. Okay, what is the reverse bias voltage? It's just the gate with respect to the drain. That's P+, that's N, so that's our reverse bias voltage, VGD. Okay, so the depletion region width at the drain is when X equals L, is basically given by the equation we saw last class. Okay, just that, where we have the reverse bias voltage with the negative sign there because the reverse bias voltage in all what we will talk about will itself be negative. So negative and negative will do the positive, so there's no problem there. Okay. Now, the only assumption we did was we assumed that the contact potential was small. Remember, in the actual equation, there's a V naught here. But we assumed that the applied reverse bias voltage is in absolute terms, much larger than the contact potential, which is typically the case. Because remember, the contact potential typically is pretty small, as long as the doping is reasonably high. Okay? So anyway, so we have this very simple equation. Okay? Now we can calculate when pinch-off happens, because we need to know what that saturation current is, essentially. So we're trying to figure out when the pinch-off happens. Geometrically, it's very simple. It's when the depletion region reaches that point. Okay? Then H of x equals L, which is the remaining part of it, goes to 0, or when the depletion region becomes A. Okay, pretty straightforward. You plug that in there, and you get an equation for the voltage. Okay, so Vp essentially is the gate to drain voltage, which is the reverse bias voltage when pinch off happens. Okay, essentially it comes by plugging A into there, W there. And Vp is QA squared ND over 2 epsilon. Vp is basically minus VGD. Or you can think about it as minus Vg plus Vd. Referred everything to the ground with respect to the source. The source is grounded. Okay? So now we know at what voltage will the pinch off happen. So when does that saturation happen? Okay? It depends, as you can see, on the area square of the width. The depth of the, I guess it's the width of the channel, okay, and the doping in the N-type region. So if I want the pinch off to happen sooner, I dope it less and make the channel smaller. Okay, which gives me an interesting thing, right? If I have the pinch off happen smaller, I can have the transistor work at lower voltages. So think about what that means when you say pinch off happens faster. It means that this voltage can be smaller, which means that I can operate my transistor at a lower voltage, which means that I can use less power for my circuits. So that gives you an idea of what things people try to do, for instance, to make low power circuits. If you want to have less heat dissipation, things like that, or if you want to have if you want to extend your battery life, for instance, you want to draw very little power. So that gives you an idea of what one can do, for instance, right? You reduce doping. You make A smaller. But of course, reducing doping has other implications. We won't talk about that for now. Okay. So I have an exercise for you, which is basically down here. What happens if Vg becomes positive? That is, the gate to drain junction is forward biased. So take 30 seconds, talk to your neighbors, tell me what you think. Okay? Okay, do you have any thoughts? I forgot your name. Mark, are you Mark? Okay, go ahead. No, actually, no, not you. Actually, yeah.
We were saying that it was just a long time before the pinch off button.
Okay, it's a good way to think about it. Anyone else? Any thoughts? Yeah.
I think my thoughts are that another change that would happen is that there would be some drain from the gate to the source.
Current flow, you mean?
Yeah.
Yes, that's a good point. Yes. Anything else? Okay, so those are more detailed than what I was thinking about, but from a very simple perspective, the simplest thing to think about, of course, the P plus N junction becomes forward biased, which means, what does that mean? That means you will inject holes from the P plus to the N type. Okay, you will inject carriers. Okay, and the depletion region decreases. Okay, so you are basically getting rid of the depletion region to some extent, and you are providing more carriers. So obviously current will go up, and as he pointed out, there will be a gate to source current. But Importantly, you lose control. Okay? The current will flow all the time. Right? So if I do forward bias, the flow, then I will have a gate to source current, which is basically exponential. Right? So I have very little control with my gate to source voltage on the total current that flows through. Okay? So instead of having a simple linear curve, you'll have this exponential curve and you lose control. In other words, you cannot really use that as a switch or an amplifier. Okay? So the proper operation for a junction field effect transistor is when the gate to channel is always reverse biased. It's important. Not always the case for other devices. For the bipolar junction transistor is the opposite. You have to have forward bias. In this particular case, it has to be reverse biased. Okay? Yes?
I'm not sure that I understand why it would work as a switch.
The reason is that you remember what you're trying to do is you want to apply a small signal to the gate and you want to monitor the current. Okay? Independent of the drain voltage. You cannot do that because you will have current flowing irrespective of it. So the channel will basically act as a resistor with no control from the gate at the end of the day. Because you don't have a depletion region. The current will just flow.
Oh,
The gate has no control, right? The gate just provides more current. It cannot reduce the current. Okay? So essentially, you will just get a huge current flowing through with a very small spikes from the gate if you inject because of injection of the carrier. Okay? So it's important to remember that the field effect transistor, under normal operation, has to be reverse biased, such that you have gate control for amplification and switching. Again, to reiterate, there are three things that are important here. The gate voltage, which is the control, the drain voltage, which is the input, and the drain current, which is the output. Okay? Keep those things in mind because we will change those when we talk about different devices. Okay, now we can take that. Okay, I have to walk you through this. This is a little busy, but let's start here. Okay, let's look. It's the same geometry as before. Let's look at the voltage drop across the length of the channel. It kind of looks like that. And let's look at a very small infinitesimal region in the channel of length dx, and look at what the voltage drop is there. Okay? So the voltage drop here is dVx across a distance of dx. How does that relate to the drain current? It's related by the resistance. Okay? So the current ID is voltage drop divided by resistance. Right? The current is the same across, so there is no differential here. The voltage changes across the channel, so you have differential. Okay? What is the resistance? It's basically the resistivity times the length, which in this case is dx, divided by the area of cross section. Right? So this is nothing but area divided by rho, dv dx divided by dx. Okay? And the area is essentially this area, so this cross-sectional area, right? So you have H. Of course, the depletion region doesn't contribute, there are no carriers, so you can ignore that. So it's H of x, okay, this much, times however much it comes out of the page, which is Z. You can think about that as a width. Okay? Or the depth, depends how you call it. So it's H, function of x, multiplied by Z, divided by rho. Okay? Oh, this is a factor of 2 because there's 2x, top and bottom. Okay, that's clear, right? So it's h there and h there. So it's essentially the current is given by voltage drop divided by the resistance of that little strip. Okay? Rho is, of course, the resistivity of the neutral end region. C is the depth of the channel. Don't think about that. It's the depth. Okay? Then we make what's called the gradual channel approximation, which essentially is that the h of x is a linear change, which is a reasonable approximation. So h of x essentially goes as a minus w of x. It's a straight line. Okay? W of x we know from before. We plug that in with respect to the gate voltage. Local gate voltage with respect to the drain. Okay? Because as you move across this channel, this voltage drops. So of course, the local reverse bias voltage is Vg minus this voltage. Right? Vg is the terminal on the P plus side. This voltage is what's on the N side. Vg minus this voltage is the reverse bias voltage. And this voltage is dropping, so you have a term here. It's here. Okay? Vg minus Vx with the negative sign. Okay? So you plug that in. Now you have a relationship of the height of the channel to the applied voltage, the control voltage, the gate voltage. Okay? Vp is just the pinch-off voltage. So you can see it just comes from those constants. Now, going up here, going up here, you can put those two equations together. You take this, plug it in here, okay, and you get this differential equation which relates the voltage drop to dx. Okay? Then you can simply do an integral. Pretty straightforward because the boundaries are very simple. On this side, dx is just from 0 to L. Here, the Vx goes first from 0 to Vd. Okay? And it's just a square root, so it's a fairly simple integral. You get 3 over 2, right? Voltage dependence on 3 over 2. So now you have a current voltage characteristic. ID depending on Vg, which is that family of nonlinear curves that we saw before. So now we have a mathematical relationship which does that. ID, the drain current, is related to Vg, the gate voltage, and Vd, of course, the drain voltage. So you have everything you need. The three quantities we talked about, ID being the output, Vg being the gate, control voltage, and Vd being the input voltage. Okay? So this is the characteristic of a simple FET transistor. Okay? Okay, now we have to understand how yes? It's a pinch-off voltage. This is the voltage when the pinch-off happens, and it's a constant. So just think about it that as a constant. Because remember, it only depends on the geometry of the channel, the doping, and so on. So it's just a number. Okay? G naught shown here is an important parameter. It's essentially the conductance of the channel, and we'll come back to that. It's important. Okay? It's related to the amplification. Okay? Of course, it's a simple number. It's easy to understand. It is 1 over the resistance of the channel. Right? Inductance is 1 over resistance. It's just 2Az over rho L. And you can see, calculate it. It's very simple. Okay, everything else, you get some sort of complicated nonlinear equation. Okay, so now we can plot the family of curves by plugging in different VGs and different VDs in MATLAB. You can plot these curves. It's pretty simple now. We can solve everything. Okay, now let's look what happens at pinch-off. Because transistors are usually operated beyond pinch-off, as we will see. So let's see what happens at pinch-off. Vd minus Vg equals Vp is the definition of pinch-off. That's when the voltage and the depletion regions meet. Okay, and the current, essentially what we talked about before, was that the current becomes independent of the drain voltage. Okay, so it doesn't behave like a resistor anymore. It becomes like a saturated diode in a sense. Okay? Or a reverse saturated diode. Remember, in reverse saturated diode, we talked about reverse saturation current, which is independent of applied voltage. The same situation here. Of course, in this case, the current is much larger than in a reverse bias diode. But the situation is very similar. Okay, now if you assume that beyond pinch-off, the current doesn't change, which is what we assumed before. So it's okay to assume now again. We will change that assumption later on. The saturation current now is just, you take that equation we saw before, this expression here, and plug Vg minus Vd equals Vp, which of course Vp is a constant. Okay, so you plug that in, and you get a very simple expression, okay? Which looks like that, which of course has no Vd in this case. So it's independent of the drain voltage, as we assumed it should be. It only depends on the gate voltage. Okay, Vp, remember, is a constant. So the only variable here is the gate voltage. Okay. Now you can see this gives rise to a family of curves. So each of these curves, then Vg is 0, Vg equals minus 1, Vg equals minus 2, Vg equals minus 3, is essentially this equation, where we put numbers into Vg, gives you different curves. Okay? And the pinch off, which is shown here, okay, is essentially this ID saturated as a function of Vd, okay, but Vg also, so you can relate Vd and Vg here, so you can see that happening. To the pinch off voltage, essentially, okay? So this plot is essentially where the pinch off happens. Okay? So you can see as Vg becomes more negative, the pinch off happens sooner, which of course makes sense from our intuition, because we expect the depletion regions to come in, touch faster, sooner. Okay? Smaller drain voltage. And indeed, that's what the math tells us, so it makes sense. As Vg becomes more negative, the saturation current decreases also, so the whole thing, the family of curves goes down, which is this ID sat is essentially this saturation current, right? If you take a line and draw it across here, that's the ID sat. As gate becomes more negative, this ID sat jumps down really fast. And that's the amplification. Okay, small changes in gate give large changes in current. So you can see mathematically now we can see the amplification. And of course that's also the same as switching, right? You go from very small to very large. A small signal voltage at the gate can be amplified if operating in a saturation regime. So for an amplifier, the transistor is operated not only under reverse bias, but also under saturation. Okay? Keep those pictures in mind. Now, we will, to quantify the saturation, we define a factor, which is essentially an amplification factor. How much of an amplification happens? You come in with some small signal here, you get out a large in current. What is the change in current, drain current, with respect to change in gate voltage? That's the amplification factor. How much of a gain have you gotten? Right? And that is a name, and that's called the transconductance. It's conductance because it's current versus voltage, right? It's inverse of resistance. It's conductance, but it's not a regular conductance, it's a differential conductance. It's the marginal increase in current for a small increase in voltage. So it's called the transconductance. It's a mutual transconductance in this case, okay? So that's the GM under saturation, is the rate of change of the saturation drain current with respect to rate of change of the gate voltage. With respect to the gate voltage. Okay? So again, the input is the gate voltage in this case, and the output is the drain to source current, which is basically what I drew here. This is time. Okay? This is time signal. Okay? You come in with some small signal, get out with some large signal. It's amplification. It's sort of like what you did with an op-amp. Okay? Now we can calculate this very easily by taking the derivative of this expression. So we have ID sat is related to Vg here, and everything else is a constant, so you can take the derivative. It's pretty straightforward. You do it, you get something which looks like that. Okay? So the transconductance depends on Vg. So you have a nonlinear amplification. So higher the magnitude of the gate voltage, the higher the amplification you get. Which will become more intuitive later on, because you have to give energy to get amplification. That's where the energy comes from. Okay. The G naught here is the conductance of the channel. Remember, 1 over the resistance of the channel. Same thing we saw before. There's a figure of merit for an FET device. It's also called mutual transconductance for a unit depth, which is GM over Z. And it's essentially, it's easy to see from this expression. Just one more. Because G naught has a Z here, so you just get it to the denominator. So it just gets rid of one dimension of the channel. So you can compare different FETs. For instance, you can make different geometries. For instance, in the New York Times article, they actually made FETs in the third dimension. Here we're still talking about surface. Okay? So you can compare different kinds of FETs. FET is a field effect transistor. Okay. So experimentally, the drain, saturation drain current is related to the gate voltage as shown here, and that's experimentally determined. But IDSS is the saturation drain to source current when the gate voltage is 0, essentially. It's the highest drain to source saturation current you can get. You make it more negative, that goes down. Okay. And that's what's basically, these dots should be lined up here. So that's basically what this curve is. And you can see it's almost like a parabola, which is basically what that is. Okay. Okay, now there's two assumptions that are very important in the most advanced transistors, which actually break down. Okay, and this is very important, and you should know this because almost all the transistors today actually break this assumption. Two assumptions break down when the channel length is small, which is scaling for Moore's law. We talked about it before. Channel lengths have the transistors, so the way they make the transistor smaller is by making the channel length smaller. Okay, which is obvious because the channel is long, it takes up lots of area, smaller than that. You would expect it to be faster and so on. But unfortunately, when you make that smaller, some of the things that we talked about before, the two key assumptions break down. So we have to talk about them. And this is basically shows Moore's law to some extent. You can see a transistor. This is not a field effect transistor, but it's representative. You can see a channel length here. Okay, it's about 90 nanometers in 2003. Goes down to 65 nanometers, 45 nanometers, 32 nanometers, and in this device, which is from the New York Times paper, it's an article, it's 22 nanometers. Now, these are very, very small numbers, okay, as we saw before, okay? Now, what that does, the reason they do this, first of all, is because you make them smaller, you can pack more of them in the same area, right? So you get higher density. Of course, channel length gets smaller, your switching speed also gets smaller. So you can switch faster too. We'll talk about that. Now, there is a problem. The problem arises because when you have a very small channel length as shown here, even a very small voltage which is applied across the source and the drain can cause very, very large fields, electric fields. Right? It's a very small region, but even a small voltage can create a huge field. When you have very high electric field, we saw before that the mobility of the carriers can saturate. So instead of having V, the velocity of the electron being mobility of the electron multiplied by the applied electric field, we get some saturation. This is a linear curve, right? This is like that. So instead of being like that, at some point it will saturate. And that, of course, will affect the current, right? The current electron. We'll look at that quantitatively in a few minutes. This can cause electron mobility to saturate and thereby increases resistivity to increasing voltage, which means that as you change the drain voltage, the current can change. But the assumption we made was the drain voltage after saturation has no effect on the drain current. In other words, if you go back to this family of curves here, you will get a slope here, which is a little bit problematic. What that means is that this amplification will be distorted, if you think about it. So you have problems with your signal processing. That's not so good. So you have to take that into account. Also, as the drain voltage increases above pinch off, the channel length decreases. Okay, so that's very easy to understand. So let's go back to the old picture here. Okay, let's look at pinch off. Where's pinch off? Oops. Yeah, here. If I increase the drain voltage further, this will start moving left. Okay, because More and more regions will become more depleted. They will start touching, which means that my channel where I have carriers gets smaller and smaller. And that effect, of course, will become more pronounced when the whole channel length is very, very small. Yeah, at some point, the whole channel will disappear, right? So, of course, there is some effect. And that's an easy effect to understand, but you can see that the current has some effect. So the drain voltage will have some effect on the current. Okay. Let's see. Okay. So as the drain voltage increases above pinch off, the channel length decreases, and the saturation current can increase, not remain constant. You again get a slope in that what we supposed was constant, okay, which again basically relates to distortion in your signal. So you have problems. So when you have very small devices, you have to actually account for that. So we won't account for that right now, but you should be aware of it. Right? That's basically my point. Okay. The last topic in this for today's lecture is exactly the same. So it's very simple, except that now instead of having a p-n junction, we have a metal semiconductor junction, a Schottky barrier. Exactly the same. Remember, all the math's exactly the same. We know this. Okay. The only thing we changed, we replaced the p plus region with a metal. And why would you do that? We would do that because it's simpler to fabricate, it's smaller, so you can integrate it easier, and it's faster. Right? Those were the reasons for the diode, exactly the same reasons here. Okay, so let's look at it in some detail. So metal semiconductor FET is called a MESFET, okay, metal ME. It's the same as the JFET, junction FET, but using a reverse bias Schottky barrier as the junction. Okay. So this is a simple example, which is, in this case, it's gallium arsenide substrate. You have an N-type gallium arsenide channel, okay, channel here. You have a drain contact here, a source contact here, and your gate contact here. And this gate contact is essentially a metal to a semiconductor Schottky barrier. So you can see it's very simple. It doesn't require any doping. You don't need to put P plus or anything. Just put the metals down and do some annealing. It's very simple to fabricate. Okay, so it has some significant advantages. The key points are, of course, that this has to be a metal semiconductor Schottky barrier. So it's like a p-n junction, and it's reverse bias. Exactly operates the same way. You get a depletion region as shown here. Okay, aluminum on N-type gallium arsenide would do it, for instance. Okay, and the other important points are that these two contacts have to be ohmic. You don't want them to be junctions. Okay, otherwise you will rectify your signal. Right? You don't want that. So you have to make sure that those are ohmic contacts, and typically they use gold germanium. Gold is okay for gallium arsenide. Okay. So the key points, why would one want to do it? For high frequency operation. Very fast circuits, microwave circuits, things like that. Okay. Also, one can also handle high power applications, so high current can be handled this way as well. It's a small device size, and you can see it's small because all you need is essentially a piece of metal touching the semiconductor. There's no junctions, no other doping involved, which requires lithography. Okay, so it can be quite small. The channel lengths can be very, very small, so you can have high device density. Okay, very, very high density. Used primarily for gallium arsenide integrated circuits. So it also has the advantage that the carrier mobilities in gallium arsenide is typically much higher than in silicon. So you get fast, very fast operation. The reason this is not typically used in our CPUs and so on is because gallium arsenide is very expensive. Silicon is just so much cheaper. So otherwise, one would want to use this. But in applications where cost is not a concern, for instance, in satellites or military applications and so on, they use this sort of stuff. Okay. In fact, as I mentioned before, there's a company in southern Utah which actually sells these things. Gallium arsenide substrates for use in all kinds of niche applications, mostly military related. The device characteristics are exactly the same as JFET, so we don't actually need to work through the math again. It's exactly the same, right? Because we know a Schottky barrier is the same as a P plus N junction under reverse bias. Forward bias is different, but reverse bias is exactly the same. So we don't actually need to do anything. It's exactly the same equations. The physics is exactly the same. You get pinch off, same thing. Okay, in this case, you see there's only one gate, so the pinch off happens when the depletion region reaches the insulating substrate. Okay, so you can see there's an insulating substrate and there's an N-type gallium arsenide. Gallium arsenide is not conducting here. You get N-type, when the depletion region reaches there, you get pinch off. So it's just the depth of that N-type doping which determines how much that A, 2A in our channel before. Okay, so, but other than that, it's exactly the same. Okay, I think we will stop here, I want to hand out the midterms, and I'll finish up the rest on Thursday. We'll start with MOSFETs hopefully on Thursdays because we have a lot to cover. Okay.